Okay, let's unpack this.
Let's do it.
We are diving deep into the foundational architecture of artificial intelligence. I'm talking about artificial neural networks.
Right, and this isn't a deep dive into, the latest flashy large language models. This is the history you actually need.
Exactly. We're tracing the lineage of the fundamental component, the artificial neuron, from its initial biological inspiration all the way to the sophisticated models that we use today.
And our sources for this give us a really spectacular view of how simplicity evolved into sophistication. We're walking through three um, distinct conceptual leaps,
Okay.
starting with the static McCullough-Pitts neuron,
Mhm.
then the trainable perceptron, and then the mathematically smooth Adeline,
Which all leads up to the big one, logistic regression.
which is an essential classifier that's still used everywhere.
So our mission is to understand the conceptual breakthroughs, the aha moments that let these simple pieces of software finally learn.
It's all about things like continuous error minimization and robust optimization.
Right. So if you've ever needed a shortcut to understanding the bedrock of machine learning, how a system decides if a transaction is fraudulent or if a sound is a command, this is the core mechanic you need to master.
Let's get into it.
We have to start this entire journey way back in 1943, a surprisingly early date, I think, for the origin story of the artificial brain cell.
It really is. Two scientists, Warren McCulloch and Walter Pitts, published the first concept of a simplified digitized nerve cell, the McCulloch-Pitts neuron, or MCP neuron.
And what's so fascinating here is just how reductionist it was.
Totally. They looked at a super complex biological neuron and just asked, what's the absolute simplest mechanism here that allows it to compute? They modeled it after a single nerve cell in your brain.
Right. And if you think about how a biological neuron actually works, it gets thousands of tiny chemical signals at its dendrites.
Those are the inputs.
It gathers all those signals up in the cell body.
And this is the critical part.
Mm.
If that accumulated signal hits a specific trigger point, a threshold, boom, it generates an electrical impulse.
An output signal that shoots down the axon.
It either fires or it doesn't. It's binary.
And the MCP neuron is basically that concept, but in a digital context. It's, at its core, a simple logic gate.
Yeah, you put in signals, it calculates a weighted sum. If that sum crosses a fixed threshold, the output is a 1.
Meaning fire
Yeah.
or yes.
And if it doesn't, the output is 0, don't fire, or no.
It's a beautiful mathematical concept, but as you said, it was static. It was pre-wired.
It could execute logic, but it couldn't learn from its mistakes.
Yeah.
And that is where Frank Rosenblatt stepped in 1957.
He built on this foundation.
He did. He published the concept of the perceptron learning rule. He figured out how to make that static neuron adapt.
Okay, so the core task for this new perceptron was still binary classification.
Right. We wanted to predict whether some data point belongs to class 1, let's say spam, or class 0, not spam.
And how does it see the data?
Yeah. Well, the artificial neuron calculates what we call the net input. It's actually pretty simple. It just takes the weighted sum of all its inputs. So every feature, x, gets multiplied by a weight, we.
And it adds a little offset, the bias.
Exactly. That result is the net input, which we call z.
And then the perceptron applies its decision function. And this is that hard, unforgiving unit step function we talked about, the strict threshold.
Yep. If z is positive or 0, output is 1. If z is negative, output is 0.
The goal of the learning process, then, is for the algorithm to automatically find the perfect set of weights, the W's, that lets it draw the correct line between the two classes.
And that is the true conceptual leap, the learning rule. It's what dictates exactly how those weights adjust when the prediction is wrong. It's a self-correction mechanism.
A mechanism that relies on the difference between what the computer predicted and what the true answer actually was.
Precisely. Let's think about the mechanics without getting too deep in the math. The size of the weight change depends on two things. First, the learning rate.
Which is just a small number, often called eta, that controls how big of a step the algorithm takes.
Right. And second, the error, which is then multiplied by the actual value of the input feature that, contributed to that mistake.
So if the perceptron gets it right, the prediction is correct, the error is 0, and nothing happens.
The weights stay the same, no reward, no punishment.
But if it makes a mistake, that's when the nudging happens. So say the true class was 1, but the perceptron said 0.
The error is positive. The learning rule looks at this and basically says, okay, we need to increase the net input next time to push it over the threshold. So it increases the corresponding weights.
The weights are literally being pushed toward the correct answer.
They are. And conversely, if the true class was 0 but it predicted 1, the error is negative.
So the learning rule says we need to decrease the net input.
Exactly. It applies a negative correction, pushing the weights away from the wrong prediction. It's a remarkably simple but powerful idea of self-correction.
It sounds really elegant, but then we hit a massive roadblock.
A huge one.
Hmm.
This system had a critical limitation. The perceptron learning rule is only guaranteed to converge, to find the right weights, if the two classes are perfectly linearly separable.
Wait, so what does that mean? If the data points are all tangled up, like if you can't draw a single straight line to perfectly separate the spam from the not spam,
The perceptron would never settle down.
they would just fail.
The weights would just oscillate forever, constantly trying to draw a dividing line that just doesn't exist. You'd have to manually impose a maximum number of passes or epochs just to stop it from running indefinitely.
That sounds incredibly fragile, impractical for the messy real-world data we actually have.
It was. And that fragility, that dependence on perfectly clean data, is what made it a dead end for a while.
So that critical failure, that rigid all-or-nothing step function, is what drove the next conceptual leap.
It had to. And in 1960, just 3 years after the perceptron, Bernard Woodrow and Ted Hoff introduced the adaptive linear neuron, or Adeline. And Adeline is really where we leave the simple biological mimicry behind and step onto the road of, true machine learning.
How so?
Because it provides the foundation for basically every optimization routine we use today. It introduced the idea of minimizing a continuous cost function.
Okay, so the input calculation was the same, that weighted sum, z. What changed that made it so revolutionary?
The change was subtle, but just profound. Adeline uses a different type of activation function when it calculates the error.
Okay.
The perceptron used that hard discontinuous step function for the error calculation. Adeline, however, uses a linear activation function.
Meaning the output for the error calculation is just the net input itself?
Exactly, the raw value.
Why does that matter so much? Why is a linear continuous error function so much better than the perceptron's binary one?
Because the continuous function is smooth. Imagine the error landscape of the perceptron as like a jagged, messy mountain range full of sharp cliffs. You can't use calculus to find the best way down.
Okay, I see.
Adeline's error landscape, on the other hand, is a smooth, gentle valley. By defining the error as the sum of mean squared errors, or MSE, which is a continuous and differentiable function, we can now use the most powerful optimization algorithm there is, gradient descent.
Gradient descent. Okay, this is the mechanism that lets the computer find the lowest point of error, the sweet spot, without just, checking every single possible weight combination.
Right. It's often compared to climbing down a hill blindfolded.
And it's the heart of modern machine learning.
It is. Because the MSE cost function is continuous, we can use its derivative, the slope of that hill, to know exactly which direction to step. In each step, we move in the opposite direction of the gradient, always trying to find the minimum loss.
And the step size is key here. That's controlled by that crucial hyperparameter, the learning rate.
A parameter that you, the user, have to experiment with and set yourself.
And if you get it wrong,
if your learning rate is too large, you take these massive steps and you just jump right over the minimum. Your error actually gets worse with every attempt. It's like trying to walk down a staircase by jumping. You're just going to overshoot and fall.
and if it's too small,
Your error will decrease, but it'll be painfully slow. You're shuffling down that staircase 1 millimeter at a time, requiring thousands of steps or epochs to finally reach the bottom. It's a huge waste of time and computing power.
So the balance is everything. But even with a perfect learning rate, gradient descent can be thrown off by messy data, right?
Absolutely. Which brings us to a fundamental but so often overlooked necessity: feature scaling.
Ah, right. So if you have one input feature, like income, that ranges from $20,000 to $500,000.
And another feature, like age, that ranges from 20 to 80.
The income feature, just because its numbers are so much bigger, will completely dominate the weight updates.
It creates a biased learning environment. So we use a technique called standardization.
Standardization.
It's elegant. We shift the mean of every single feature to 0, and then we scale the data so every feature has a standard deviation of 1.
You're essentially forcing all your input data to play fair.
That's a great way to put it. By transforming the data this way, no single feature can dominate the gradient descent process just because it uses larger numbers. It smooths out that hill we're climbing and makes convergence much, much more reliable.
Okay, so the Adeline method we've been describing uses what's called batch gradient descent.
That's right. which means that in order to calculate the direction down the hill, the algorithm has to sum the errors over the entire data set, the full batch in every single epoch before it can update the weights.
That sounds computationally punishing,
Yeah.
especially if you have millions or billions of data points. You're just recalculating everything constantly.
Exactly. It's incredibly costly. And this computational bottleneck is what stochastic gradient descent, or SGD, was designed to solve.
Stochastic gradient descent. The name sounds complex, but how is the mechanism different?
The key conceptual change is that SGD updates the weights incrementally for each individual training sample instead of waiting for the full batch.
Ah, okay, so batch gradient descent is like plotting the perfect cross-country road trip, accounting for every single mile before you even start the car.
And SGD is like navigating by GPS. You take one step, check the error, update the weights based on that single data point, and then you take the next step.
So you're sacrificing a little bit of theoretical accuracy. SGD might kind of wobble around the true minimum instead of hitting it exactly for a massive gain in speed.
And the benefits are huge. First, it offers significantly faster convergence on very large data sets. But second, and this is crucial for modern tech, SGD enables online learning.
Online learning. You mean where the model trains on the fly, constantly updating as new data arrives?
Precisely. Think of a streaming service or a financial fraud detection system. The model trains continuously on new customer data without needing to store or reprocess years of old data.
So the system can adapt instantly to shifts in user behavior or new fraud patterns.
It can. And that makes SGD the operational backbone for any system dealing with a continuous stream of information.
So we've moved from a brittle, hard binary switch with the perceptron to minimizing continuous error using smart optimization with Adeline and SGD.
Right.
But Adeline's output is still just a raw numerical value. To make the jump to true modern applications, we needed to graduate from a hard yes or no decision to a measure of confidence.
And that's where logistic regression steps in. Logistic regression is still fundamentally a linear model. It still performs well on linearly separable data. But the crucial shift here is that it predicts the conditional probability that a sample belongs to a certain class.
To understand that probability, we need to talk about odds.
Right. Odds are just the ratio of the probability of a positive event happening to the probability of it not happening.
And logistic regression uses the logarithm of the odds, which is called a logit function.
And that logit function is the mathematical link. It's what ties the linear combination of inputs and weights, that z value, to the probability of class membership.
The inverse of that logic function is the absolute hero of this section, the logistic sigmoid function.
The sigmoid function, yeah.
This function takes that raw linear input z and mathematically squashes it into a value that always falls between 0 and 1.
It's named for its characteristic smooth S shape.
Ah, that's the S-shaped curve you always see in explanations.
That's the one. And that curve is the activation function for logistic regression. It allows us to interpret the output directly as a probability. Unlike Adeline, whose output could range from negative infinity to positive infinity, the sigmoid function guarantees our result is always a percentage chance.
And once you have that probability, you just convert it back into a binary prediction with a simple threshold. If the probability is, say, 0.5 or greater, a 50% chance or better, we classify it as 1.
Otherwise, we classify it as 0.
And this is the so what moment, right? This connects everything back to real life.
It really is. The ability to estimate class membership probability is vital in high-stakes fields. Think about medical diagnostics. It's not enough to tell a doctor, yes, the patient has the disease.
You need to say, there is an 85% probability they have the disease given these symptoms.
Exactly. That confidence score is what's necessary for decision-making. Logistic regression gave us that confidence.
So what does this all mean?
Well, we've traced the history of machine learning classification as a story of really increasing mathematical sophistication and practical utility. We started with the simple biological mimicry of the perceptron, which failed when data got messy.
Then we moved to Adeline.
Right, recognizing that continuous differentiable cost functions were the key to systematic learning using gradient descent.
And that journey from a binary switch to continuous error minimization and then finally to a probabilistic output, it established the foundational techniques.
Including fast optimization methods like stochastic gradient descent that underpin every complex neural network you interact with today. These simple models are truly the great-grandparents of modern AI.
And our journey highlighted something essential. The success of all these learning algorithms, whether it's Adeline or some massive modern network, it depends entirely on the features being standardized, being forced onto equal footing.
It does. Which, it raises an important question. If the very best learning systems we can invent rely so heavily on making sure the inputs are perfectly standardized with a zero mean and unit variance before they even begin to learn, how crucial is the often overlooked step of data preparation in all forms of learning, both machine and human? Something to consider next time you encounter a complex set of sources that you need to master.